Let me begin with a word of prayer. Dear Father, we thank you for the weekend, time to relax, refresh. Pray you be with us today. Help us to glorify you what we do this day, Lord. In your name I pray. Amen. So let me just address the mistakes in the notes that we found last class. This won't take actually that long. I think I managed to find both of the grievous mistakes in my notes during class last time. I fixed example 17 last time with a kind of long argument, which was, I think, fine. But another way to fix example 17, to make it into a reasonable problem, would be just to choose a equals to 1 instead of a equals to 0, in which case I don't beg the question of, is 1 over x to the fourth defined at 0, right? So if I just do that, then example 17 is repaired. Just choose a equal to 1 rather than a equal to 0. Everything else went through just fine. The next example, which I was leery of, because, of the previous one, I think it's fine. And so this example is actually kind of more advanced. See, the trouble with this integral is that I have x to the fourth minus 8x squared minus 3. And so, my intuition is that this is convergent because it's like what? It's like p equals 4, right? I mean, it's like that convergent integral of dx over x to the fourth. So the question is, can you compare it? Well, to compare it directly, you need to, make this thing smaller than 1 over x to the fourth, right? So, but the trouble is, I'm subtracting from x to the fourth, right? So strictly speaking, 1 over x to the fourth minus 8x squared minus 3 is greater than 1 over x to the fourth, all right? Because I'm removing, I'm making the denominator smaller, right? So I can't do a direct comparison. So I went to some more sophisticated arguments here. What I did was to find the roots for this quartic by making an x squared substitution, I think. And anyway, they end up being this, so I can factor x to the fourth minus 8x squared minus 3 into x squared minus lambda 1 times x squared minus lambda 2, where lambda 1 and lambda 2 are as above, all right? But here's the thing. If you're beyond 3, right, if you're beyond 3, then x squared minus lambda 1 is larger than 1, right? So I can trade this quartic is bounded above by what? By this quadratic. And lambda 2 is what? Lambda 2 is negative, right? So this has a larger denominator than that because that's a minus, which is a plus. So in short, I can compare the given quartic actually to 1 over x squared. And so then I can use the comparison test with that if you want. But I mean, as you can see, the inequalities involved here are a little bit more subtle than the ones I've talked about in the last class, right? So it's kind of always a give and take with the comparison theorem. Is do you want to work harder on your inequalities to work your way to something easier, or do you want to just face a harder integral with an easier inequality? I mean, it's kind of a give and a take. So I would say this is a somewhat sophisticated example for you guys. But the fix to this example, I kind of indicated in class last time. I posted this in the announcements, right? But here's the fix. I wanted to decide whether the integral from 1 to infinity of e to the x over e to the 2x plus sine x converges or diverges. So I decided that, in fact, my choice of comparison last time was ridiculous. Instead, I should compare to e to the minus x, basically. So if you just ignore the sign, which is between plus or minus 1, right? The sine of x is just tiny compared to the exponentials involved after x gets really large. So my target here was to compare to e to the minus x. I didn't quite get that. So the inequality that suggested itself to me was that this is less than that, right? Because if you think about it, sine x, first of all, I argue that e to the 2x plus sine x is positive, all right? So at least the fraction you're looking at there is bounded below by 0. But then the other thing is, sine x is what? It's between plus or minus 1, right? So this denominator, the absolute smallest it could be would be what? E to the 2x minus 1, right? So if I make the denominator as small as possible, then that makes the fraction as large as possible. Consequently, this is an upper bound for that expression. But the thing is, what's on the right-hand side there, I can actually integrate that. Now, it's not easy, but I can do it. Well, easy, not easy. I mean, eye of the beholder, I suppose. But here's the integral. So this is make a e to the x equals u substitution. That gets us to du over u squared minus 1. I partial fractions that thing. I integrate. It gives me that. Laws of logarithms gives me this. 1/2 log of e to the x minus 1 over e to the x plus 1 plus a constant. And then I tackle the improper integral here, taking the limit as t goes to infinity of the definite integral from 1 to t. And so that when I plug in the t into the antiderivative, I calculate it up here. I get this and that. But the beautiful thing about this is as t goes to infinity, the thing inside the logarithm goes to 1. So we're left with 1/2 log of 1, which is 0. And only the second term actually contributes. I flipped, you see this? I flipped it. E to the minus 1 over e plus 1 to e to the plus 1 over e to the minus 1. All right? And that's a good thing because after that's done, we're looking at the logarithm of a number larger than 1, which is positive, which makes sense, right? Because this is the integral of a positive function. The answer ought to be positive, right? If you get the integral of a positive function as a negative number, you should probably question your calculation, right? But this one worked out. And so then, we've proved that the integral of this larger function converges to that value. It follows then by comparison that the integral of e to the x or over e to the 2x plus sine x, in fact, converges, moreover, to some number between 0 and whatever that is. So, sorry, I had a very grievous logical error in the notes. When we got to it on Friday, it was very vexing to me, you may recall. And then on the same day as I find out this horrible error, I give you back your test with grades that you're not particularly fond of. This is not wise. I should bring you ice cream today or something, right? I mean, like it's too early. Bring us donuts instead. Does it feel like more like a donuts kind of class than ice cream? Am I wrong? No? Like just curve our test instead. Yeah? No, okay. So that's pretty much it for improper integration. I mean, I have this one other example over here, which I think I fixed it. So I had to fix this example as well because, of course, I learned that the integral of e to the x over sine x plus e to the 2x is actually bounded above by log of e plus 1 over e minus 1, like so. And the 2 cancel because I put a 2 out front there. So you can, if you have two things that are convergent, and if you add them together, you get a thing which is also convergent. And there's like a natural, when these infinite integrals converge, some things that you're used to still make sense, like twice the integral. Integral of 2 times a function is twice the value to which it converges, things like that, right? The thing you got to be careful for is infinity minus infinity is not, you can't just be, it's not 0. I mean, this, for example, integral of 1 over x minus x, on paper, right, if you separate these integrals, you get minus infinity for the first one, and you get infinity for the second one. Well, wait a minute. Vice versa, I think. Let's see here. Yeah, minus and, well, I think that's just minus infinity minus infinity. Ay, ay, ay. What do you guys think? Actually, I mean, I'm not wrong that it's not right, but it's not right how I've said it's wrong. See, because the integral from 1 to, oh, wait a minute. Oh, I was thinking 0 to infinity. Sorry. Integral from 1 to infinity, that gives me like a log of infinity, which is positive infinity. And this gives me a minus 1/2 x, minus 1/2 t squared as t goes to infinity. This is okay. It's okay. Let me not talk myself out of it. Anyway, all I'm saying is both of these integrals separately diverge, and so the whole thing doesn't work out, okay? The integral of 1/x minus x is not a convergent integral. All right, and then just so we all feel a little bit ill at ease, I ended the chapter with an example that we don't know how to do. But on a more serious note, there are techniques beyond what I show you, all right? So there are problems which we don't have the technology quite to handle. This would be one of them. Integral from 1 to infinity of dx over x sine x. I don't know how to solve this problem with the techniques of this course. And I honestly forget if this converges or diverges. I think we answer the question of this integral in complex analysis, all right? So there are more things past this to learn, but I will shut up. So, oh, let me put this away. Oh, come on. Come back to us. So with that, we begin our discussion of sequences, which I think is a somewhat more relaxed topic than what we just got to. I mean, we ended with the hardest part of the improper integration material, which to me is the comparison. Why is the comparison, applying the comparison test to problems, why is that a hard problem? What makes it hard? Yes, inequalities are weird, I think is a good summary, yes. So it involves both inequalities and limits, which I would say that most of us still need to do work on, right? All right. Probably don't want to attend 495, right? I think you'd like to. Here we go. what is it? 5904. All right. So, next story arc. So, this course, you know, there are parts of this course which seem to make people use this term quantum leap. This is a horrible expression. Like, a quantum leap is very, very small. But what do people mean by quantum leap? They mean a large and disconnected step, right? This is very, very much not a quantum leap. Anyway, stupid show. Anyway, so sequences and series is the next sort of big topic in here, all right? And let me just give you kind of a bird's eye view of what we're going to do. To start with, are we done with this? We're done with this. I'm going to turn it off. What'd I do? Oh, yeah. Fair enough. Thank you. So, there we go. So here's the lay of the land going forward. First, we need to understand what a sequence is, all right? A sequence is essentially a list of numbers, all right? And so we have to understand sequences and their limits, all right? This is essentially the same as looking at functions. It's a lot like looking at functions of the reals and looking at the limits as x goes to infinity. All right, so like a lot of the math here you've in some sense already seen. All right, it's just that we're replacing x with a natural number. So that's the first thing, sequences and their limits. Once we've got that settled, that allows us to define numerical series. Numerical series In other words, a series of numbers is formed by taking a sequence and just adding up all of the terms in the sequence, one after the other. But to define a numerical series carefully, we must already know how to take the limit of a sequence. All right? So series are built over sequences in this sense. To define a series converging or diverging, that will be defined in terms of a corresponding sequence of partial sums converging or diverging. All right? And then we have to settle that. Numerical series is, there's a bunch of convergence and divergence tests. There's like a half a dozen of them. There's a lot to say there, all right? I should warn you, this is a difficult topic, all right? It is, I would say, qualitatively different than anything else you've done in calculus up to this point. It involves logic and the use of theorems. It's not about a calculation, it's about making a decision. Does a given numerical series converge or diverge? So, I mean, if it were up to me, if I had complete control over the curriculum, I wouldn't even put it in this course. Because to me, it's a much more sophisticated mathematics than anything else we're doing here. But it is customary for it to be in this course. And everyone who's taken this course has had to work their way through this. But I'm just warning you, it's hard. All right? Not impossible, but hard. So beware of that. What I'm trying to say is if you're frustrated on it, when we get to it, don't feel bad. And then after that, we talk about power series. Power series. And power series are a new way to represent functions. And so this is where we talk about the Taylor and the Maclaurin series and things like this. The power series, that's where this material really pays off to calculus. Because by finding a power series representation of a function, we're able to extend our treatment of integration to many, many more functions than we could before. All right? And it also gives us a powerful program of approximating functions with polynomials in a systematic way. All right? So this is where we're going. Our ultimate goal is really this. Right? But we have to do our due diligence and work through these things before that, okay? There's also other payoffs, like understanding numerical series carefully gives us an understanding of what real numbers look like, right? Questions like 0.99999 repeating, is that really equal to 1? We're able to not only answer that question, but answer it with authority in here, all right? So, sequences. What's a sequence? Any questions, though, before I begin? So I would say, generically speaking, a sequence is a function from the natural numbers into a set. But we could be more specific here. A real sequence is a function, let's say a, from the natural numbers into the reals. Where a of n is denoted a sub n for n equals to 1, 2, 3, da 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 da. So, we typically talk about f of x, right? This would be like replacing f of x with f sub x. So it's kind of a weird notation, but this is the standard notation. For a sequence, we don't write a of n, we typically write a sub n. All right? Also, we sometimes refer to them like this: a sub n equals 1 to infinity. This is a sub 1, a sub 2, a sub 3, dot, 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 dot. Is sometimes referred to as a sequence. I would say if you want to be picky, that this, to me, this is the range of the sequence. You see why I'd say that? Why is that the range of the sequence? I would say technically that's the range of the sequence, yeah? Right. But, you know, you've already been exposed to these kinds of confusions in your pre-calculus class, right? We tell you there's 4 different ways to represent a function. Sometimes we'll say a function's its graph. Well, I guess this isn't really the graph. I mean, what does a sequence look like? What would a graph of a sequence look like? Actually, literally the graph of a sequence. And we almost... Let's see here. So let's look at y equals to, I don't know, 1 plus the sine of n for, you know, n equals to 1, 2, 3, so forth and so on. What would that look like? I regret my choices. Let's make that sine of n pi over 2. It's more exciting. Otherwise, I'm going to have to get a calculator out and start thinking. But sine of multiples of pi over 2, that I can calculate with my head, you know? So, like, what's the sine of pi over 2? One, right? So 1 plus 1 is... I'll do it a little bit, not to scale. There we go. And then when we plug in 2, what do we get? Sine of pi, which is 0, right? So that just becomes 1 plus 0, which is 1. How about 2? 3, rather. 3, sine of 3 pi over 2 is minus 1. So minus 1 plus 1 gives me 0. Sine of... let's see, plug in 4. 4 over 2 is 2, sine of 2 pi. 0, so 0 plus 1, 1. When I get to 5, I get sine of 5 pi over 2 is 1, so I get 1 plus 1 is 2 again. And then I go back to 0, and then I go back to, we go back to 1, I go back to 0, I go back to, see what's going on here, right? But a sequence, it's what? It's not continuous, right? It's not continuous. What do we say about such a, what word do we use? Instead, we'd say it has a discrete, right? Discrete graph. And by that, qualitatively, we mean that the points in the graph are like disconnected, right? You can isolate each point with like a little open set if you wanted to, right? Like there's some kind of disconnection between the different points in the graph of a sequence, right? But it seems like there's a connection between this sequence and a function. Like what function is this sequence I just wrote on the board connected to? I heard a sine. I think we can imagine, right? Y equals to 1 plus the sine of pi x over 2, right? This is a continuous extension of the sequence. All right, so what is a continuous extension of a function? Well, what's an extension of a function? If we had A1 is a subset of A, let's say, and f is a function from A to, let's say, the reals, just to keep it simple. I should probably just put a b over here. I'm trying to be a little bit general here. A function from a to b, then f restricted to a1 is a mapping from a1 to b, where f restricted to a1 of x is just equal to f of x for x in a1. So we talked about this a little bit before when I talked about open. Remember, we talked about like the idea of a local inverse and taking the sine function, restricting its domain so that it becomes invertible, or the cosine function restricted to 0 to pi becomes invertible, or the tangent function restricted to minus pi over 2 to pi over 2, not included, becomes invertible. So here, f bar a1, this is the so-called restriction of the function to a1. This is f bar a1 is f restricted to a1. In this case, f is an extension. It's an extension of the restriction. So if you can view one function and another related by restriction, then the function with the larger domain is called an extension of the function with the smaller domain. So what I'm suggesting here is concept given sequence A from the natural numbers to the reals, we may extend to f from the reals. Well, let's say from, we don't need the reals, right? Let's just say f going from 1 to infinity to the reals by what rule? How should we define this new function f in terms of the given sequence A? Let's see here. I'm going to say f restricted to n is equal to a. In other words, f of n will just be equal to a sub n. But then that leaves you with the question, okay, well, that's wonderful. So you've defined a function to be equal to the given sequence at natural numbers, but what about all the other points, right? What about 1.1? What about 1.2? What about 1.3? What about everything between the natural numbers? What are you going to do with those? And so this is the interesting thing. The interesting thing is not unique. And yet, I mean, this is an example of this, right? This is a continuous extension of a sub n equal to 1 plus sine of n pi over 2, all right? Now, why am I talking about this? I mean, you might wonder. There's a theorem which says if f from 1 to infinity to the reals is an extension, I should say continuous, a continuous extension of a sequence A, then the limit as x goes to infinity of f of x is equal to the limit as n goes to infinity of a sub n. Now, I have committed a cardinal sin of mathematics, which is what? I've used something I have not defined. Have we defined the limit of a sequence yet? We have not. What do I mean by limit of a sequence? I'll put the careful definition back over here for you guys. Definition, a sub n goes to L, or the limit as n goes to infinity of a sub n is equal to L if for each epsilon greater than 0, there exists a big N in the natural numbers such that little n greater than or equal to big N implies the value of a sub n minus L is less than epsilon. In such a case, we say a sub n converges to L. What was the definition of the limit as x goes to infinity of f of x converging? You guys remember? How did we define limit as x goes to infinity of f of x equals to L? What would that mean? If L is a real number, how did we define that? What that meant, right? Definition. For each epsilon greater than 0, there exists big M in the reals such that x greater than or equal to big M implies the absolute value of f of x minus L is less than epsilon. I can draw a picture. So if you've got some function and it could misbehave, but eventually it settles, let's say suppose that eventually it settles, towards some horizontal asymptote, then that here's my y equals L. And so what this theorem is saying is if you pick an epsilon band around the alleged limiting value, right? Let me just draw it in green. Draw it in green. Like so. But what the theorem what the definition says is you pick any any epsilon band, no matter how small, right? You can find a point at which, if you go beyond that point, values of the function are no more than epsilon units away from the limiting value, right? So in my picture, what's the choice of M? On the graph, you can kind of see it. It's, somewhere in here would be a legit choice of M. See, if we look at any, say, x out here, then this, it's hard to see, but if you blow it up right in there, between L plus epsilon and here's, this distance right here, that would be the value of f of x minus L. And that would be less than epsilon, because epsilon is the distance between the center red line to the upper green line. So the definition for a sequence converging is the same. But what's the difference? you don't have a continuous graph, right? You just have this sort of discrete spectrum. So like a sequence could be something like this, right? And the sequence I'm drawing in green, and I'm foolishly attempting to graph in blue right now. This sequence would take the original black function that I've drawn as an extension, a continuous extension. All right, and so what the theorem says is that the limiting behavior of the continuous extension of a sequence and a sequence, they share the same fate. They share the same limit. Furthermore, if a function continuously extends a sequence, all right, and that function has a limit which does not exist, guess what? The sequence also, what? Like if the function was always tracking with the sequence, well, definitely if I'm certain if the function has a limit which exists, certainly the sequence must also have the same, whatchamacallit here, same limit. Also, if the continuous extension of the sequence blew up, right, if the function limited to infinity, it seems like the sequence would also limit to infinity, right? That's a reasonable conclusion here. So why do we care about this continuous extension of sequences? How about this? If we have a sub n equal to n e to the minus n, what's the limit as n goes to infinity of this? As n goes to infinity, we're looking at what type? Infinity times 0, right? So here's the proper argument. I say, okay, so extend continuously to f of x equal to x e to the minus x. Is that a continuous function? Is polynomial times an exponential continuous? Search your heart. You know it to be true. Yes? Okay, good. And then what can we do with the limit as x goes to infinity of x e to the minus x? How do we calculate that? I'll just repackage it ever so slightly. Limit as x goes to infinity of x over e to the x. Now, why would I do that? I did that, so now it would be, yeah, L'Hopital's, right? Now it is of the pattern that is susceptible to L'Hopital's rule, right? It's type infinity over infinity. So I can apply L'Hopital's rule, and I get what? 1 over e to the x, which is 0, right? Thus, n e to the minus n goes to 0 as n goes to infinity, since x e to the minus x goes to 0 as x goes to infinity. So let's see another example. What if we had a sub n equals to e to the minus n sine of n squared? What's the limit of this sequence? Yep.
So after the 0, so the thus there, what's that notation?
Which notation? This one here?
Did I just say as?
Yeah, that's as. I can't. I should never try to write this low on the board. My handwriting degenerates. Don't even, if we had boards that were like down here, it would be completely unreadable. If I try to write down here, it's just hopeless. But yeah. So this is a notational. So guys, we have options. N goes to infinity of a sub n equals to L is equivalent syntax to a sub n goes to L as n goes to infinity. Both of these have their place. Both should be used. As makes your sentences flow most nicely. In the same way, the limit as x goes to infinity of f of x equals to L is interchangeable with the statement f of x goes to L as x goes to infinity, right? Just two different ways of packaging the same mathematical statement. Yeah.
So does that mean like the nth term approaches L as it goes to infinity, or like?
Yes, the nth term approaches L as n goes to infinity. Yeah. So why didn't I just do L'Hopital's rule on the sequence directly? Because it's discrete, right? You can't differentiate something discrete. Now, if you watch previous years of this course, and indeed this year of the course, I will allow you an abuse of notation. All right? I'm a relatively easygoing fellow, believe it or not. And the limit as n goes to infinity. So here's another notational scheme. You could write it this way. You could say, well, that's the limit as n goes to infinity of n over e to the n. Fine. And then extending n continuously, apply L'Hopital's rule. All right? And so then, see, but without that little qualifying phrase, I really should take off a point, right? And I'm sure some professors would probably disagree with me using this notation. They would say something along the lines of, if you allow students to use this catchphrase on the side, they're just going to use it like a lucky talisman without understanding, and they don't really understand that you can't differentiate a discrete variable. What is it? Yeah.
What's the thing going to be?
L'Hopital's rule. Oh, I'm sorry. Yeah, this means applying L'Hopital's rule. And I put the type, I also justify what kind it is, either 0 over 0 or infinity over infinity there. This is not my notation. It was taught to me in Calculus 2 myself. Yep.
So we do like an H or an equal sign, or do we have to do that?
Oh, you were taught H?
Yeah.
Hey, that works. The hospital rule? Yeah, yeah. By the way, because the other thing is without the S, but with a circumflex over the O. Which is correct, with the S or without the S and with the circumflex over the O? Which is the correct spelling of L'Hopital's rule? The correct answer is that, yeah?
I just have a question.
Oh, yeah.
I don't understand what extending means, like extending n continuously.
That means I'm using this theorem. I'm taking my sequence, I'm replacing it with a function, which is a continuous extension. Then I'm applying L'Hopital's rule to this function of a continuous variable where calculus makes sense. L calculus 1, I'm applying L'Hopital's rule. I am then finding the limit and then transferring back to the sequence, all of that.
Okay.
It's an excuse of using this theorem without writing it out.
Okay.
Is all. Finally, this one, -1 less than or equal to sine n squared less than or equal to 1, right? Hence, minus e to the minus n less than or equal to e to the minus n sine of n squared less than or equal to e to the minus n. Yet plus or minus e to the minus n goes to 0 as n goes to infinity. Hence, by squeeze theorem, the limit as n goes to infinity of e to the minus n sine of n squared equals what? Yet, yeah. Or if you like, observe. So the limit as n goes to infinity, e to the minus n sine of n squared is equal to 0. Right, so tomorrow I will give you a systematic rundown of what we know for limits of sequences, like linearity. We know, we still got the squeeze theorem. Because of this theorem, basically everything we know about limits at infinity, all of those rules will transfer over to limits for sequences. And we'll go from there. Thanks, guys.